A Kubernetes deployment process usually begins simply. You write a declarative YAML manifest to define the desired state of a single microservice, and the cluster executes it. But as an architecture scales up to 20 or 30 distinct microservices, that simplicity fractures. You now have dozens of deployment and service files to maintain. Then you factor in your deployment pipeline. You have to duplicate that entire manifest structure across development, testing, UAT, and production environments. Very quickly, your manageable configuration files multiply out into an overwhelming wall of static text blocks. This massive duplication creates a severe operational bottleneck. Because the files are static, an update to a resource limit in development might not get copied to production, resulting in configuration drift. Engineers are forced to duplicate code and manually edit hard-coded strings across hundreds of files, increasing the statistical likelihood of a critical human error. The Kubernetes ecosystem addressed these scaling issues with a package manager called Helm. There is a common misconception about how Helm actually operates. It is strictly a client-side tool. The Kubernetes API doesn't know what a Helm chart is. It only receives the final, compiled YAML that Helm generates. If you are familiar with NPM for Node.js or pip for Python, Helm provides the same operational utility, but specifically for K8's infrastructure. Standardizing your manifests into dynamic, parameterized packages allows you to manage hundreds of microservices through a single configuration interface. To understand how this parameterization works, we have to look inside the structural anatomy of a Helm chart directory. At the root level, you find chart.yaml holding simple metadata. The power comes from separating variables and logic. State is contained in values.yaml, defining parameters like replica counts. Logic lives in the templates directory, holding the raw manifests. To bridge the two, we parameterize the template files, stripping out hard-coded strings and replacing them with variable references. Using Go templating syntax, the rendering engine reads replica count from the left, dynamically injecting that value directly into the deployment template on the right. But if a pipeline executes and that configuration parameter is missing, the deployment will fail. To prevent this, we set fallback instructions using a pipe operator. We pipe the value integer into full chart. If blank, the engine automatically injects a safe default of 2. This robust architecture forces engineers to follow the don't repeat yourself principle. You write the deployment logic exactly once. By isolating variables, a single master template inside the chart can be reused to spin up an infinite number of specific deployment environments. Injecting basic parameters is straightforward, but standardizing naming conventions across dozens of interconnected manifests requires a heavier tool. If your service accounts, deployment labels, and ingress routes don't share matching strings, the cluster rejects the communication paths. Simple variable injection cannot ensure that global coordination. For this, Helm provides the _helpers.tpl file, an engine designed for housing reusable functions. Here, engineers use Go templating syntax to define custom logic blocks that generate precise strings. We define a function, let's call it appName, that evaluates environment variables and outputs a standardized string, like exam portal. Once defined, that single function can be globally invoked by any manifest. The template uses the include command to pull the exact output directly into its metadata. But generating text dynamically introduces a risk, violating YAML's strict indentation rules. If a helper function generates a multi-line string and misaligns it by a single space, the resulting file triggers a fatal JSON parsing error. We solve this using formatting controllers. Adding a hyphen strips away empty lines, and an indent aligns the text perfectly. Mastering whitespace control and building robust helper functions is what allows a chart to generate valid, production-ready infrastructure. Once the chart is compiled locally, the focus shifts to executing those manifests against the live K8's cluster. A standard kubectl apply command is stateless. You push the file and the cluster creates the resources, but the command line tool forgets about the transaction immediately. Helm operates differently, grouping your resources into a release, a persistent, version-controlled record of that specific deployment instance. The lifecycle begins when you run the primary installation command against your target directory. Running Helm install compiles templates, applies resources, and creates revision 1 inside the cluster. Suppose traffic spikes, and you need to scale up the application using a specific configuration file built for your development environment. Instead of reinstalling, you execute the Helm upgrade command, passing the valuesdev.yaml file. Helm analyzes the active deployment, applies the new replica count, and generates a new sequential node, revision 2. Behind the scenes, K8s is natively storing this differential state history within its internal secrets. Helm quietly maintains a detailed ledger of every configuration change. By tracking state differentially, Helm provides a centralized audit trail for every change made to your cluster's resources. That ledger becomes critical during high-stakes scenarios. Imagine you run an upgrade. The syntax compiles perfectly, but a faulty application image fatally breaks production. During an active outage, manually hunting down the exact YAML values to change or trying to rewrite Git commits takes far too long and carries too much risk. Instead, you run the Helm history command to diagnose the active release and identify the last known stable state. Once identified, executing a rollback to revision 1 instructs Helm to instantly rewind the cluster state, restoring your exact previous replica counts, image tags, and parameters atomically. This instant recovery is only possible because of the architectural constraints we discussed earlier. The isolated configuration state and the differential tracking secrets allow Helm to pivot the entire application structure in seconds. This standardized structure also allows you to tap into a massive community ecosystem. Because the anatomy of a chart is standardized globally, engineers rarely have to build complex logging, monitoring, or database manifests from scratch. Instead, they rely on centralized public repositories, like Artifact Hub, which hosts thousands of pre-configured modular technology stacks. The modern deployment workflow is abstracted. You pull a verified OCI chart, inject your custom values.yaml to override the defaults, and instantly deploy a resilient infrastructure stack. By standardizing configuration logic, enabling atomic state rollbacks, and tapping into a global repository of packages, Helm provides the mechanics needed to deliver automated, enterprise-scale continuous delivery.